Hi, welcome to my FPGA tutorial video. This is the second video of the series, and in this video we're going to implement a very basic design based on DE10-Standard, which is just to blink an LED. So first, let's begin. First, we're going to launch Quartus. Quartus is, well, now Intel Quartus used to be Altera Quartus. It is the IDE for Intel or Altera FPGAs. So first we start a project, and then we'll just put that on desktop. Let's say called the first FPGA. Good. Create a new folder. Next. Yes. Empty project. Next. We're going to add some files later. Now we're going to choose the chip. Now we're going to cyclone 5, and now we have the SX. Unfortunately, the XX family actually has transceivers, has a dual-core ARM processor, and has FPGA fabric. But on the particular board, DE10-Standard, there was no any breakout pins for the transceivers. So despite we have 9 on-chip transceivers, but that's effectively disabled on this board. But anyway, just for the ARM processor and for the fabric, that's really nice board. Anyway, so now we're going to choose the FC6 D6. That's the chip, and for this particular board, we're using the C6 speed grid. And next, nothing more. We don't want to customize any of the tool changes. We just want to make a very basic design. So now we have the design. Now we can create a top level file. I always prefer the top level to be schematic capture, and then we are going to have the Verilog or whatever language that's for the actual module implementation. But for the top level, I always want to have the schematics. Okay, now we have it, and we save the file. Save as first FPGA.pdf, great. And then we create the actual LED blinking counter module. So we create a Verilog file. Okay, now you can type your code here. In this particular case, I already have that done. Let's cut counter. We open that. We copy them. Go back and paste. Now here we're counting to 500K, and that means we're looking for, let's say we want to have 2 blinks, so on off in 1 second. Then that means we have to count this number for 4 times. So we need a 2 MHz clock. First save the file. We just call the let's say counter. Alright, then we can implement that in the top level. We save that file. Yeah, and I forgot. For this particular file, we have to create a symbol, so we can draw that on the top level schematics. So file, create, and create a symbol. And then it shows, okay, it has successfully analyzed the input and output, and the file seems to be correct, and it generated the symbol file. Now we go back to the BDF project. Now we can see our counter. Great. Let's zoom in a little bit. Okay. And then we want to feed a clock to this thing. According to the datasheet of this board, we don't have a 2 MHz clock on board. We only have 25 MHz, and it's not really that. I mean, we can divide the clock using a Verilog block, but I also want to demonstrate how to use a PLL, using that to generate a very high quality clock from the 25 MHz reference clock. So let's begin. Now I have already opened the IP catalog, but in case you don't have this window, we can find that from tools. We have the IP catalog, and then you will open this panel. Now for the basic functions, you will see a clock, PLL, and Altera PLL. Double click that, and let's name that as PLL. And open the Mac wizard, and that will take some time. let's see. Because we know from the datasheet of the board, with 25 megahertz, then a clock distributor, and also PLL, and then we generate 24 megahertz for the USB port. Then we generate 25 megahertz for the ARM processors, and 50 megahertz goes to 4 clock inputs. So in this case, we just use the clock 0P, and that's assigned to AF14. Okay, so now we know the input reference is 50 megahertz, and I want 2 megahertz output. The actual frequency will show what is the actual frequency number is generated, because you don't have all the combination of all possible frequencies. So this wizard is smart enough to give you a number of very close in the range, and then you can choose from which exactly you want. For example, if I want to have 1 megahertz, the PLL will tell me that's impossible. You can generate a minimum 1.17 megahertz. So that's not going to be possible to get exactly 1 megahertz. But for another frequency, let's say, if you can generate it, you can just choose the number that's bang on. But if you have to choose a number that's not really bang on, then you have to choose one that you think fits your feature need the best. And I don't really care about the log output, so that will be it. Finish. We'll take some time to generate the module, and after generating the module, you will have a Verilog top a block for this module, and then you always will have a schematic symbol, so you can put that in your top level schematics and double click. And we have the PLL, great. And we'll put this here. The output 2 megahertz goes to the clock input, and then the we'll put some pins. We have the clock input, we have the reset, and the LED. Also keep in mind that for this particular PLL module, the reset is actually high enable, and for this counter, the reset is actually a low enable. So we are going to use inverter, because we know that the push button is actually low enable. As we can see here, the push buttons are low enable. So that means that means we have to negate the signal on the reset pin for the PLL. So we add primitives, a logic, and there will be a NOT somewhere. Here it is. And that's it. Then we will have to have 3 pins for the reset input, reference clock, and LED. And it's not logic, it's pin. We have 2 input, 1, the other one, and the 1 output. The output goes to the LED, and we just name it. How about just LED? Oops. Great. And we have, let's put it here. Yeah, just the reset. Therefore, put the ground. And for the reference clock, I don't really care about the depth of polarity. And that's clock. Alright, and I think we are pretty much done for the top level. And now you want to assign the pins. Unfortunately, that's not possible because Altera doesn't know whatever pins you have. And now if you just say assign pin planner, you won't see the pins. So to first synthesize your top level design. Let's run that. It'll take some time. The first one will take quite some time, but at least we have the progress bar. That's one thing I really like the Quartus, because you know, for Vivado you only have something's running, you don't really have a progress or something. But for Quartus, you have this nice progress bar to know what is exactly happening right now. And also a lot of features are exposed in Quartus, just from user interface, graphical user interface. But for Vivado, there's really, at this place you have a TCL console, and a lot of things you just have to type the command. But it's more like a preference. Some people may like the Xilinx workflow, some people may like the Altera workflow, but I work with both, and I like the Altera workflow more. It's probably just because I use Altera from the very beginning when I started using FPGA, so I'm just more used to use that. Maybe that's the reason, but anyway, it's more like a personal preference. So now we are at time quest. Actually, you can define a time quest input file. You can define the clock. You can do a lot of things to tell the time quest what exactly clock you're doing, and what kind of constraint you want to have, so you don't have this error message. But this is just a very basic introduction of how to use Quartus, and I will skip that part. And now you can assign the pins. Pin planner. Now we can see the pins. We know that the push button, let's say use the key 0, that's AJ4. The reset is gonna be AJ4. And then the clock is AF14. This is a very simple logic, and it really doesn't matter where you put the clock. But if you have a fairly complicated design, then actually the IDE will actually the compiler will actually detect which signal is actually a clock, and they will try to map the clock to a global buffer. That's called a clock tree. And in that case, you have to, if you have a lot of different clock loads, then you really want to put that clock into a dedicated clock pin. In this case, AF14 is a dedicated clock pin, so that would guarantee a better quality of clock. In this small design, it doesn't really matter, but it's just a good practice. And then we have the user LEDs. Yeah, let's say LED 0, that's AA24. And now we have AA24. And since the board operates on 3.3 volt at this moment, we are going to use a 3.3 volt logic level. Great. And now that's the pin assignment. Let's close it, and let's give it a go. We'll start everything from somehow like scratch, so it will take some time. Let's see, it's now trying to fit everything into the limited logic tiles. Place and route. Let's see what's happening. Yeah, I didn't derive any clocks. That's that should be defined in time quest, but just as I said, it's really a simple design, and 2 MHz is pretty much nothing, so I'll just skip that part. Synthesis, fitting, and now generating the bit stream. Now we can see we're using 27 ALMs, and totally we have 110K logic elements, which are distributed in 42K ALMs, and we use only less than 1% of them, somewhere like 0.5%. It's cool. Now we can see if the design works. Now we go to tools. Oh, by the way, before we start, we will have to first make sure that we are in either we're in active 0 mode or in whatever mode that, because later we are going to try to program the design actually into the FPGA board and program that into the EPCS device. So whenever we are next time powering up the board, the board will automatically load this design. So because we're going to use the EPCS device, we should put it into this AS mode. That's from bit 4 to bit 0 is going to be 10010, and that corresponds to a dip switch on the board, which is this one. This dip switch. Okay. So we set a dip switch, and then we program the board. Power up the board, and tools, we have programmer. And for the first time user, you have the hardware set up, and you have to detect the device. But since I already done that, you can see that we have the SOC device, and then we can auto detect devices. Choose the proper device. Because there are different devices showing the same JTAG ID, so you will have to choose from a number of different devices. And choose the proper one. Okay, now we have the programmable device. The JTAG chain goes to the ARM processor and then goes to the FPGA. But in this case, we only care about programming the FPGA. So click the FPGA, click change file, and in output files we have the SOF file. Great. And we choose program. Click start. Successful. And now we can see the blinking LED. You can see that there are also some other LEDs. They are weakly illuminated. And that's because we have a weak pull up on all the unused I/O pins. And now I'll show you how to get rid of these. So let's go back to the design and assignment, device, and we have the device and pin options. And here we have unused pins tab. We go to that and set that to all tri-state without the weak pull-up. Okay. And now we can re-implement the design. And this time we should get rid of all of these pull-up resistors. It said lock port is not connected because we just hit that port. It's all expected. Let's see how it works. Now we're still in placing routing, and after showing how to blink the LED, I will also show you how to actually write the program, permanently write the program to the EPCS, so that your board can run the same design whenever it's powered up in AS mode. Now we're generating the bit stream, and we're almost done. Okay, the time quest, we don't really care about that. We're not doing any of the time analysis. Okay, it's done. So we go to Tools, Programmer, and we go to the device, D6. We select the proper file and check the program, and let's go. And now we get rid of all of these weak pull-up resistors. That's great. And then I'll demonstrate how to actually write that to the EPCS. The programmer actually provides a feature to directly program to the EPCS, but this particular board doesn't support that feature. So we have to actually program to the EPCS through the FPGA. And there will be an IP block on the FPGA called flash loader, and that's provided by Altera. So how to do that? Let's say file, convert. We're going to convert a JIC file. That's output format. And then we choose the proper configuration device, EPCS 128 in AS mode. And flash loader, we can add a device, and that's IP block I was talking about. A device using a Cyclone 5 and SX66. Yeah, D6. Make sure it's the proper. And now we have the SOF data. We add our JTAG file data. Great. And now we can generate the JTAG indirect configuration file. Will take a while, but it's not really that long, depending on how fast your computer is. Now we can program that. Now you can auto detect. Yes. And watch here. When you are loading the JSC file, it will automatically recognize the EPCS device. You have to check. You want to, let's say you can erase that EPCS, and then we won't have any of the configuration, or we can just override from program configure. So let's say I want to first remove all the features of the board, so we can verify that's actually weird, because it's already running a blinking application. So we first erase that and see what happens with a blank EPCS. Let's say we start. And before you click start, you just have to double check you are in the correct deep switch configuration. I already checked mine, so let's see it start. Now it's gonna take some while. It goes to somewhere like 30% or so, and then it's whoosh, goes to 100%. Let's see. Yep. And now we have a blank device. We can reboot the board, and we'll see the weak pull-up everywhere and no functions at all. That's just the default or blank configuration of this chip. And now we can actually do the proper programming. Uncheck erase and check program configure, and that will configure the file we specified before. And let's start. This will take some time. It will take a considerable amount of time, so it's, let's say it will take maybe 30 seconds. And let's just wait with fingers crossed. So the way the JSC works is actually the JTAG first downloads a EPCS writing algorithm to the FPGA chip, and then it will talk to the FPGA chip and say, okay, with that particular IP block, okay, I'll feed you in some data, and you put that data into the EPCS chip. So that's why it's called indirect programming. And in this way, you can actually program the EPCS without having directly connection to the EPCS device. You just have to program through the standard JTAG interface. And now we're at 36%. That's actually writing the file to the EPCS. Now it's successful, and we can reboot the board. Now we can see the blinking LED, and also the GPL is doing its job. When I press it, the PLL is reset, and the counter is also reset. And now we don't have any behavior of the board. And we release the button. Now we can see the blinking is working as expected. Alright, thank you for watching this video, and please subscribe and thumbs up.